In this video, we'll continue solving spectra problems, solving structure from spectra. Here we're going to have the IR, the mass spec, the proton NMR, and the carbon NMR. So, as usual, let's begin with the molecular formula that we're given from the mass spec here. So the best thing to do is to first determine the degrees of unsaturation, which tells you how many double bonds, pi bonds, or rings that are present in the structure. So the formula for degrees of unsaturation is 1/2 the number of hydrogens if the compound was saturated minus the number of hydrogens that are actually present minus any halogens plus any nitrogen. Okay, so now determining the number of hydrogens if saturated is 2 times the number of carbons plus 2. So for our case, the degree of unsaturation here will be 2 times 4 plus 2, that's 10. That's the number of hydrogens. We just solved for number of hydrogens saturated, plugging in 4 for the number of carbons. Then we subtract how many are actually present, which is 9. Protons that are actually there. There's no halogens, so we don't need to subtract for x, but we do need to add 1 for the nitrogen. So this is 10 minus 9 is 1, plus 1 is 2, divided by 2 is 1. So there is 1 double bond in this structure. Now, our IR is a bit unusual because we have this peak, which kind of appears to be a carboxylic acid peak, even though it is somewhat shifted to the right from what we would normally expect it. Because remember, carboxylic acid groups are, they have that OH feature, and that OH stretch will usually be slightly above 3,000, even up to like 3,500 in wave numbers. But it will overlap more significantly with the CH stretching, sp3 CH stretching that occurs around 2,900. It will overlap more than a free alcohol will. A free alcohol will have a more smooth peak that is easily distinguishable from the sp3 CH stretches, but for a carboxylic that is not the case, so this is suspected to be a carboxylic. Now, it is a little bit confusing as well because we see a 1600 stretch here, which is a little bit too low of a wave number to be a carbonyl. But if this is a carboxylic acid, then we would expect this to also be a carbonyl stretching. And perhaps these are also carbonyl stretches as well. We'll have to use a little bit more data from the carbon NMR and proton NMR to confirm, is this actually a carboxylic, or do we have to reconsider the IR stretching here? Because it's possible a carbon-nitrogen stretching also occurs in this region around 1600 when you have a nitro group that's like this. So there is a possibility that we have this feature as well, or instead, rather, we'll have to determine based on the other spectra which one is more likely. So with that, then let's move to the carbon NMR and see if it tells us anything more concrete about what's going on here. And fortunately, it does. We see a quaternary carbon. We know that this is quaternary because it does not appear in the depth spectrum. And this is a perfect region for a carboxylic acid carbon. The quaternary carbon of a carboxylic acid occurs around 170 to 180. We're right in that range, 182 maybe. So that is definitely a carboxylic acid carboxylic acid carbon. And then these are all CH2s. But they're CH2s in different environments, which tells us that there's no symmetry. How do we know that? Well, it's because we have 4 peaks. We have 4 carbons and 4 peaks. If there was symmetry, we would have less peaks than carbons. This is not the case. Each carbon has its own unique peak, so there must be no symmetry. So this suggests that perhaps this carbon here is bound to the nitrogen as it's further downfield compared to the rest, and then perhaps this one is adjacent to our carboxylic, and then this one is stuck in the middle between these other two. So we would have a feature like this ignoring the protons right now. So let's move to the proton NMR to see if it corroborates the claims that we've made so far. So first thing you want to do here, anytime you have a question like this, they are not telling you the proton integration. They're simply giving you the actual measurements, so you'll have to integrate that to the number of protons yourself. So to do that, you need to use a ruler and literally measure the bottom of that line to the top of the line. So how I do this when I have only an inches ruler is I'll measure by 16ths. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, maybe 10 and a half. We'll call this 10 for simplicity, 16ths of an inch. This one we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 10 as well. And then this one is also about 10. Which makes sense, right? Because if we go to our carbon NMR, we know that we have CH2s. We have 3 CH2s, so we would expect that integration to be equivalent amongst those groups. So that's exactly what we see here. We have 3 CH2s. Now you may be wondering, well, if these are 3 CH2s, we had 9 protons to start with, so where are those? This is where you have to keep track. Here they tell us that you have 3 protons that are exchangeable with the solvent that are present here. So therefore, these are 2 hydrogens, 2 hydrogens, and 2 hydrogens. So that's how we do that. So since these all worked out to be 10 each, how you would do this if it wasn't so clear is you would add these up to get your measurements. So this would be 30, and this is 30 for 6 hydrogens. So divide by 6 to get per hydrogen measurements, and this is going to be 5/16 per hydrogen. So then 5/16 times 2 is 10/16, and we get 2 hydrogens per peak, and that makes perfect sense, again, because it's corroborated by the carbon NMR. Okay, so now let's see if what we thought from the carbon NMR is matching the proton splitting. So we see 3 unique CH2s, so again, supports there's no symmetry. We see that the furthest upfield, or the lowest number of CH2 here, is split by 4 neighbors. So that CH2 must be sandwiched between 2 other CH2s. Right, so this peak is that one. So what else do we know? Well, we know that this is in the range to be adjacent to the carboxylic, which we've confirmed from the carbon NMR. So this makes perfect sense to be this carbon, because this proton peak here is a 2 hydrogen triplet. It's split by these 2 adjacent protons. Makes perfect sense, it matches up. And then lastly, we just have the nitrogen to account for. That must be adjacent or bound to this carbon, because it is also a triplet, so it's only adjacent to one of these CH2s to split it into a triplet, and it's at a ppm chemical shift of around 3, which also matches because it's adjacent to nitrogen, which is more electronegative and electron withdrawing than the carbonyl peak, like being adjacent to the carbonyl. So that is our structure. So we have 1, 2, 3, 4. Here's our structure, and then we can label each peak corresponding to each structural feature. So here we have, let's call this A, this B, this C. A is adjacent to the carbonyl, so that's going to be this middle peak. B is the one sandwiched between the 2 alkyl groups, so that's going to be the lowest number, the most upfield. And then the C is bound to the nitrogen, which is furthest downfield. And then, of course, you have the 2 exchangeable protons that aren't shown in any significant way, that are the OH and the NH2, those 3 protons. And then, of course, you can do the same thing on your carbon NMR. So let's do that. Now here we have to consider all the carbons rather than carbons bearing hydrogens like we did in the proton NMR. So here we have A, B, C, and D. A is the carbonyl, which is the quaternary carbon, which is furthest downfield. B B is bound to the carbonyl, so that is going to be the one in the middle here. C is stuck in the middle between the two CH2s, so that's the furthest upfield. And then lastly, we have D bound to the nitrogen, that is the furthest downfield. And that's how you solve this question. All right, here we have the next question. So again, let's start with the molecular formula. So we have C7H8O, so let's do our degrees of unsaturation. That is 1/2 the number of hydrogens if the molecule is saturated, which is 7 times 2, which is 14, plus 2, which is 16. Minus how many are actually there, which is 8. 16 minus 8 is 8, divided by 2 is 4. So this is the perfect number for a benzene. So we should already be thinking about that when we see a degree of unsaturation like 4. So let's move to the IR to see if that corroborates what we were thinking. So it perfectly does. Here we see aryl CH groups. These are sp2 hybridized CHs that appear slightly above 3,000, which is what we see. This is above 3,000. We also see this aromatic overtone here around 1,500 to 2,000. And of course, we see C double bond C stretching around 1,600, which is present in a benzene. So that's what we know there. Is there anything else to ascertain? We can say that this oxygen cannot be a carbonyl, as we see benzene, and that is all 4 of our degrees of unsaturation. So we cannot have a carbonyl like a ketone or ester or something like this. We also don't have an OH because there's no OH splitting here, stretching at the above 3,000. So the oxygen must be part of an ether, is what we can ascertain from the lack of signals here. So, and then of course we also see this C single bond O stretching in the fingerprint region, but it's very difficult to confirm if that's definitely what we have going on. The fingerprint region is always usually a little bit of a mess, so the aryl CH in the aromatic overtone is much more indicative here. Okay, so let's move to the carbon NMR. Okay, so in the carbon NMR, we see a quaternary aromatic carbon at around 160. That is that's going to be bound to this oxygen-containing group, most likely. That's what pushes it slightly more downfield. And then we see 3 aromatic benzenes that are present here as well, that are probably not bound to the oxygen, but they are nearby in varying levels, which makes them have their slightly different shifts, which ultimately suggests that this is asymmetric. There's no symmetry here. Or let's say there's limited symmetry. How do we know there's limited symmetry? Well, let's think about this, right? We have 1, 2, 3, 4, 5 carbons. There's 7 carbons in the molecular formula, so that means there must be some level of symmetry that's creating 2 pairs of carbons to be the same. And then also we see this CH3. This is likely a CH3 that is shifted quite a bit by an adjacent oxygen. That's why it's around, 60 instead of 20 or something for a typical methyl group. Okay, so let's move to proton NMR to see if we can piece this together. So we have a singlet around 3.5, so this confirms that we have an OCH3 group, as this CH3 would be a singlet because it's adjacent only to the oxygen, and it is around 3.5, which is the typical region that an oxygen bound to a carbon would appear. And of course we see our aromatic protons, and the expansion here is most useful. So around 6.7, let's say, we have a 3 hydrogen kind of mess here, but this isn't really as messy as it appears because this is a doublet and this is a triplet. So the reality is this is a 1 hydrogen doublet, or actually it's a 2 hydrogen doublet and a 1 hydrogen triplet. Or actually, is that, yeah, no, that's right, because we have 3 hydrogens here versus 2. Yeah. So let's piece that together if that makes sense with our structure here. So we have benzene that we know that's present from the aromatic group because of all this stuff here at 6.5 to 7.5. We also have a OCH3. And then we need to consider how many carbons do we have total. We have 7 carbons total. We've already used 6 of them. So if we have benzene and OCH3, then they have to be bound together. And this is all of the atoms that we have, right? We have C7H8O. So we have 5 aromatic carbons, 1, 2, 3, 4, 5, and then 3 from the CH3 and the oxygen, of course. That's everything that there is. So does this match our spectrum? Well, it definitely matches the OCH3 group. Now we have 5 aromatic protons, and we need to consider their splitting. So these hydrogens, the mirror plane or the plane of symmetry is across the hydrogen here to the OCH3, which makes these 2 protons the same, and these 2 the same, these 2 the same, and that one different. And then of course the OCH3. So the OCH3, there's no ambiguity, that's D. Now A, you would expect to be a 2 hydrogen doublet, as it's adjacent only to B, which is equivalent on either side. So you would see one splitting partner, so 1 peak. And that's exactly what we see. So A is here. Now, when you look at the next one, B, you would expect to be a triplet, 2 hydrogen triplet, as B and B are the same here due to the symmetry. So, and they are split by A and C each, which makes them be a triplet. So in fact, this integration here is slightly off. This should be 4 hydrogens and this should be 1. As here we have the 2 hydrogen triplet as I thought as I was solving this, and this is only a 1 hydrogen peak here, which then makes sense because you have the proton C here is split by B on both sides, which would make it a triplet because even though they are the same, they are splitting a different peak, like a different proton. So as such, you would expect multiple splitting there. Now, one last thing to mention is when you have electron donating groups bound to the ring, that will shift the protons near that electron donating group upfield to lower numbers, which is why A and B are in this group of 4, because they are much smaller, they should have a smaller number because they are bound closer to the electron donating group. So that is that one, and let's look at the carbon NMR here to confirm what we just thought from the proton NMR. So here's our structure. Here is carbon A, let's say, carbon B, C, D, and E. A is definitely this OCH3 group here at about 60. B is the quaternary aromatic carbon, which is there. C then is closer to the OCH3, so we'd expect that to be slightly more downfield, and then D, and then E. Okay, and that's how you solve this question. All right, here we have our next question. So let's look at our degree of unsaturation first from the molecular formula. So degrees of unsaturation are 1/2 the number of hydrogens if saturated. In this case is 7 times 2 plus 2 is 16, minus 8 is 16 minus 8 is 8, divided by 2 is 4. So again, we should be thinking benzene. So let's look at our IR to see if that's confirmed. Well, here we clearly have an OH stretch because we have this very smooth and broad peak, which is distinct from the carboxylic, like we looked at in the first question of this video. And then we also have some aryl CH stretches above 3000, and then we do have just some sp3 CH stretching around 2900. And then of course we have the aromatic overtone, which more corroborates the benzene idea, and that's really all we have here. We have some C double bond C and a C O stretching. Okay, so let's move on to the carbon NMR. I'm ignoring the UV spectrum, but you could also get information there, but I'm going to show that you can solve this without that information. So let's look at the carbon NMR. So we see a quaternary benzene, a quaternary aromatic carbon that is likely bound to something that's not extremely electronegative because it's not shifted more into like the 160 region. So it's probably just a benzene bound to like a alkyl group. And then I should probably start with this, and before we looked at that, but this was the first thing I noticed, but you should always consider, is there a symmetry or not? And here we have 1, 2, 3, 4 peaks, and we have 7 carbons, so there is some symmetry. And actually, there isn't 4 peaks, there's 5 peaks, because if you look at the expansion of this region, which is here or here, you see 1, 2, 3 peaks. So this, what looks to be 2 at first glance, is actually 3, 4, and 5. So again, there's 5 carbons, so there's some symmetry still. There's 2 pairs of carbons that are the same. Very similar to the last question. And then we have a CH2 that is extremely de-shielded. So this is probably bound to the OH group that we recognize from the IR and the benzene, which makes sense when you consider the quaternary carbon here is not extremely downfield, and that would be the case if it was bound to a CH2 then an OH, because the CH2 is not going to shift the benzene, quaternary benzene carbon downfield very much. And then the rest of these are just the rest of the aromatic carbons that are in that structure. Okay, so let's look at the proton NMR to see if this is corroborated with the splitting. So here we have an exchangeable proton. This is clearly the OH. Then does a 2-hydrogen singlet make sense from what we proposed from the carbon NMR? And it does, because we have the aryl group has no proton on it. So actually I should draw it so you can see what I'm talking about. So this CH2 is adjacent to the OH, which does not cause splitting. And then this carbon here has no hydrogens. So that also doesn't cause splitting because there's no proton there to do the coupling and split. So as such, it makes perfect sense that the CH2 would be a singlet. Does the chemical shift make sense? Well, it's adjacent to an oxygen, which would shift it to about 3.5 to 4, but then it's also adjacent to the benzene, which is also electron withdrawing to a lesser extent than the oxygen, which is why it adds maybe another ppm shift, which puts it around 4.7, close to 5. That matches up pretty well. And then here we have a 5-hydrogen mess here at about 7.5 that are bound to the benzene, which also makes sense because the alkyl group is not going to change the position, the chemical shift position of those alkyl, of the benzene aryl protons rather, very much. The alkyl group will not. So as such, they are very close to one another, and that's why it just looks like a blob of 5 hydrogens. So that does in fact match. So let me show where the peaks are. So let's call this A, and the rest of this is just B, because it's all in one blob. Now I should mention, if you had a very strong magnet, it would probably separate these somewhat, because as you know, this carbon here should be split into a doublet, and this should be a triplet, and that should be a triplet. So you should be able to distinguish that splitting pattern in theory. In practice, you need a super strong magnet. Like this is already 400 megahertz, which is pretty strong, but you would need 600-700 megahertz to get this type of separation that we're talking about here. So, and in this case, it's not even needed to solve the structure. So there's not a huge advantage to push for something like that for a compound like this. Okay, so let's finish this up real quick and look at the carbon NMR once more. So here's the structure, and now we have the carbon NMR. So let's pair the structural features to the peaks. So let's call this A, B, C, C, D, D, and E. the carbon NMR was able to distinguish these much easier, the difference here in the peaks, so in the carbons. So here's A. B is the quaternary one, which is here. And then C is probably the one closer to the OH group. So that C is here. And then D is here. And E is here. Okay, and that is how you solve this question. All right, here we have another question. So let's start with the degrees of unsaturation, as usual. So we have 7 carbons, so 7 times 2 is 14, plus 2 is 16, minus 7 is 9, but then we also have one halogen that we need to subtract as well, so that's actually 8. Divided by 2 is, of course, 4. So again, this is very suggestive of the benzene. If we look at the IR, we can quickly see that that is confirmed because we have aryl CH stretching above 3000. We also have the aromatic overtone. We also have C double bond C stretching. And perhaps you have some carbon-bromine stretching in the fingerprint region here. So this all suggests that you have an aromatic group bound to a bromine in some way. So let's move on to the carbon NMR to see if we can get more specific. So when we look at the carbon NMR, we see 1, 2, 3, 4, 5 peaks, right? Make sure I'm interpreting this right. Yeah, this is the expansion here. So 1, 2, 3, 4. Yeah, there's 4 in this region and then 1 here. So there's 5 peaks. So again, that suggests some symmetry. Okay, then we have a CH2 group here that is that is shifted somewhat downfield, but not extremely heavily. So that means this is probably bound to the bromine. And then that means it must be bound to the aryl group because we know we have benzene. So that means likely that this is our structure, where this quaternary carbon is this one here. And then the other 3 benzenes are just the symmetric benzene carbons from that ring. So let's look at the proton NMR to see if this is confirmed. So again, we have a 2 hydrogen peak at around 4.5. That makes perfect sense for what we're proposing. This one would be at 4.5 here. Let me label it in a different color. Right, this would be the 4.5 peak because it's bound to the bromine, which would shift it around, 3.5 to 4. And then the benzene also has some additive electronegativity that shifts it downfield, electron withdrawing nature. So 4.5 makes perfect sense for that. And then, of course, we have all these benzene aryl protons that are also going to appear in the same region because our magnet here, it's only a 200 megahertz magnet, so it's even less powerful than the previous question, so we don't get significant resolution there. We just see a blob of aromatic protons. So that blob here is B, and this is A. And then we can do the same for the carbon NMR. Right here. So we have A, B, C, D, and E. So B is the quaternary, and then A is the next obvious one. That's the CH2 bound to the bromine in the aryl group. And then the remainder are kind of up to interpretation, to be honest, but C is probably the furthest downfield, then D, and then E. But the reality is that those are all so close to one another that they're just the other carbons that are present in the benzene. All right, so here is the last question for this video. So let's start as usual with the degrees of unsaturation. So here we have 1/2, 2 times 8 is 16, plus 2 is 18, minus 7 plus 1. This is 6. 18 minus 6 is 12, divided by 2 is also 6. So this likely has a benzene and then some more stuff. So let's look at the IR to see if that is the case. So we do see this 2251 stretch that's obviously labeled. This is the stretching for a nitrile. It is very distinguishable from other stretches. So we have a nitrile there, carbon triple bond to a nitrogen, and then we do have aryl CHs at slightly above 3000. So that makes perfect sense here. We have, those are our four degrees of unsaturation from the benzene, and then 2 additional from the nitrile. So that's all 6. Okay, let's move to the carbon NMR to see if we can get some more structural information. So here we see in the depth spectrum a CH2 that is somewhat downfield. This is probably bound to the nitrile. And that's why it's not extremely far downfield, because it is bound to just a carbon, not something very strongly electronegative. So then it's also bound to the aryl group, which is slightly more electron withdrawing, which would push it in the region that it appears. Next, we have 2 quaternary carbons. This quaternary is the benzene, and this is quaternary is the nitrile. Nitriles are slightly more upfield than benzene carbons. And then we see 3 additional aromatic carbons that are, we have little information about at this point, but they're a part of the ring in some fashion. So let's move to the carbon NMR, or proton NMR rather, to see if we can piece this all together. So we do have a 2 hydrogen singlet around 3.5. So this is probably what we were mentioning in the carbon NMR, a CH2 bound to the aryl group and the nitrile. That would put it around 3.5, as the nitrile and the aryl group aren't extremely withdrawing, but they are somewhat withdrawing, and then you add them both together and you'll see a peak around 3.5. That makes sense. And then of course we have all these aromatic protons that are just bunched up together. So this has to be a monosubstituted benzene, once again, with the nitrile at the CH2 group there. We know this because this is the only way to get the 2 hydrogen singlet that we see here. And then of course we have all of the benzene protons. Right? Then we can do the same for the carbon NMR, which in this case has slightly more information. But again, we have some symmetry, which is why we have less peaks than we do carbons. And we have 2 quaternary carbons. And F. So A is our nitrile, which is here. B is this group. C is the aromatic quaternary carbon. And then the rest are kind of, again, up for interpretation, but probably D and E will be slightly more downfield, as they're slightly closer to the nitrile, and then F will be the furthest upfield, which F is actually this peak, which you can't really see. It's a shoulder on the main peak there in the carbon NMR. So that is how you solve this problem. So if you enjoyed the video, please leave a like and to subscribe to the channel for more content like this. If you have a video suggestion or topic idea, please feel free to let me know in the comments down below, and I'll create a video on that as soon as possible. So that's all I have. I hope you have a great day, and I'll see you all in the next video.